Imagine a frozen wanderer from the depths of another star system barreling toward our sun at over 200,000 kilometers per hour, defying the scorching heat of perihelion and emerging transformed, revealing secrets that could revolutionize how we humans dream of interstellar travel. That's the incredible story of the Comet 3 I/ATLAS. And today, we're diving into how it survived the ultimate cosmic trial and what it means for our future among the stars. Discovered on July 1st, 2025, by the Atlas telescope in Hawaii, this wasn't just another comet looping around our sun like Halley's or Hale-Bopp. No. 3 I/ATLAS is only the third interstellar visitor ever confirmed. A rogue from beyond our solar system, ejected from its home perhaps billions of years ago, carrying the chemical fingerprints of a distant alien world. Picture it: a dusty, icy body roughly the size of a small mountain, hurtling through the void at speeds that would take it from Earth to the moon in mere hours. Its hyperbolic path screaming, "I'm not from here," with an eccentricity over 6, meaning it slingshots around the sun and flings back into interstellar space, never to return. As it approached our inner solar system, astronomers worldwide turned their eyes and telescopes skyward. Hubble, James Webb, even Mars orbiters locked on, because this wasn't just a rock, it was a time capsule from another star, venting gases like carbon dioxide instead of the usual water vapor we see in our local comets, hinting it formed in an ultra-cold environment around a long-gone sun, maybe older than our own solar system. And then came the big moment. October 29th, 2025, Perihelion, the closest brush with the sun at about 1.36 astronomical units, just inside Mars's orbit, where the heat intensifies to levels that could melt lead, the solar radiation pounding relentlessly, enough to strip away layers of ice and dust in violent outbursts. Many wondered if it would shatter like some comets do, fragmenting under the thermal stress. But 3 I/ATLAS, it endured. Emerging from behind the sun, it didn't just survive, it transformed. Observations from the Gemini North Telescope revealed a stunning shift. Its coma, that hazy envelope of gas and dust, turned from a reddish hue to a vibrant emerald green, glowing like a cosmic lantern due to diatomic carbon molecules excited by the sun's ultraviolet light. A rare spectacle that lit up the night sky for astronomers and made headlines worldwide. Laughs. Sounds like science fiction, right? But it's real. This green glow isn't just pretty. It's a clue to its exotic origins, showing compositions we rarely see in our neighborhood comets, like higher levels of carbon compounds that suggested hails from a carbon-rich stellar nursery far beyond the Oort cloud. And get this. As it swung past perihelion, something even stranger happened. Its antitail, that optical illusion of a tail pointing toward the sun, caused by larger dust particles lagging behind, not only grew to a staggering length, larger than the distance from Earth to the Moon, over 384,000 kilometers, but it flipped direction, reversing orientation in a way that baffled scientists, with Hubble images showing this bizarre reversal that defies simple explanations, prompting whispers of unusual dust dynamics or perhaps something else inside, as Harvard astrophysicist Avi Loeb speculated, though most experts chalk it up to the complex interplay of solar wind and the comet's outgassing jets. Post-perihelion 3 I/ATLAS didn't fade as expected. Instead, it brightened unexpectedly, surging in magnitude from around 13 to 11.5, visible through binoculars in dark skies near the constellations Virgo and Leo, its plasma tail and dust tail flaring in periodic bursts every 20 to 30 minutes, as captured by ESA's JUICE spacecraft, making it shimmer like a galactic firefly racing outbound at 68 kilometers per second. Why did it endure? Comets like this are built tough, frozen aggregates of primordial ices, rocks, and organics that have weathered the harsh vacuum of space for eons. Their low density and porous structure allowing them to vent gases as a natural shield, releasing pressure and cooling themselves even as the sun tries to boil them away. A survival mechanism honed over interstellar distances that would take our fastest probes centuries to traverse. But here's where it gets mind-bending. This endurance isn't just a cool fact. It has profound implications for interstellar travel. Think about it. We humans are plotting missions to nearby stars like Proxima Centauri, 4.2 light-years away, with concepts like breakthrough starshot, tiny laser-propelled sails zipping at 20% the speed of light. But the big hurdles are surviving the journey. Cosmic radiation shredding electronics, micrometeoroids punching holes, extreme temperatures swinging from near absolute zero to blistering heat near stars. 3. I/ATLAS shows us how nature does it. A natural probe that's traveled perhaps trillions of kilometers unscathed, its icy mantle acting as ablative armor, shedding layers to protect the core, its chemical makeup resilient to the void's punishing environment. By studying its composition through spectroscopy, those green emissions revealing carbon chains and possible organics, we gain blueprints for advanced materials like self-healing composites or radiation-resistant coatings for spacecraft, inspired by how this comet's volatiles sublimate to create a protective coma, much like how we might engineer volatile shields for long-haul voyages. Moreover, its trajectory teaches us about gravitational slingshots on a galactic scale. Ejected from its home system, likely by a planetary encounter or stellar flyby, it demonstrates efficient paths for interstellar hops, informing how we could use black holes or binary stars as natural accelerators for future probes, cutting travel times from millennia to decades. And the anomalies? That massive anti-tail, the flip, the unexpected brightening, they hint at internal processes, perhaps waterless outgassing, or even exotic ices like molecular hydrogen, which could inspire new propulsion ideas, like harvesting interstellar medium for fuel mid-journey, turning the void from enemy to ally. As 3 I/ATLAS nears its closest approach to Earth on December 19, 2025, at a safe 1.8 AU, about 167 million miles, offering our best views yet before it slingshots past Jupiter in March 2026 and vanishes into the galaxy. We're not just watching a comet. We're witnessing a messenger from the stars, a free sample of extraterrestrial matter that crossed light years to teach us. We've mapped its path backward, suggesting origins in an older galactic region, perhaps a red dwarf system, carrying clues to how planets form elsewhere, and by extension, how we might engineer habitats for multi-generational ships or cryogenic pods that endure the long dark. Laughs. It's almost poetic, this unassuming ice ball, older than humanity, surviving the sun's fury and glowing green as if to say, if I can make it, so can you. But the real excitement? It pushes us closer to cracking interstellar travel, from understanding durable spacecraft designs to scouting potential waypoints in the cosmos. We've sent Voyagers to the heliopause, but 3 I/ATLAS reminds us the universe sends gifts back, challenging our tech and igniting our wanderlust. So, as it fades into the night, leaving us with data that could fuel the next space age, the question lingers. If a simple comet can traverse the stars unscathed, what worlds await when we finally follow in its wake?